Hello everyone, welcome to this session on artificial intelligence and machine learning. The agenda of today's session will be attention. So before I talk about attention, let me recap two things which we discussed in last sessions. Particularly, I will give some background. I will cover some points which I explained in last session, and then will motivate the case for attention. That why we need attention. After that, I will go about talking attention, how it works, and then what are transformer models? Because these models, which are very powerful, they are based on this attention mechanism. And after that, I will give examples of two large models which are BERT and GPT. I will cover a lot of stuff in this session, a lot of technical stuff. But one thing is that there is enough supporting material. I will be posting articles on Medium. I have already posted about sequence to sequence. I will post about attention also. And apart from this lecture, it will be recorded and it will be shared. PPT will be shared and GitHub repository will be shared. And you can always ask questions in case you don't understand some concepts. Because some of these concepts are pretty complex, even it took quite a long time for me also to understand. So what I covered in my past lectures, the first issue I covered was data, that we have two types of data. We have text data and we have numerical data. And we cannot directly model text data in machine learning unless we vectorize it or we make it numerical. And we discussed about a scheme of vectorization or multiple scheme of vectorization. Now onward, we will assume that our text data exists in vector forms in this session. We just assume when we say the tokens. So these tokens are nothing but vector representation of tokens. So we'll be dealing with vector representation of tokens. And then I talked about this text data vectorization, and then ordering was there in text or in sentences. The ordering of words matters. There is a sequence. And second thing was that sentences can be of variable length. So these two requirements, they motivated us to consider recurrent neural network for machine learning. Because recurrent neural network, they have memory and they can deal with variable length sentences. So that was the case for recurrent neural network, but then there was an issue that was of vanishing gradients. So these recurrent neural network, they don't have a very long memory. Like if there are long sentences, so they forget the context. If there are 5, 6, or 7 words, they can remember. But if it's a very long sentence, they forget the context due to this very vanishing gradient. Then LSTM was introduced, which could fix that by controlling the information flow with using certain gates. So we were better there with LSTM. And once we have LSTM, we could map these variable length sentences to a fixed vector. And we could also get embedding from LSTM network also. So there are Jupyter notebook on my GitHub repository, where I have used just one LSTM layer to get the embedding. So I will explain that also. Apart from sequence to sequence or other complex tasks, this LSTM can be used for vectorizing words or even sentences. And then there was on this LSTM network, we made sequence to sequence model or encoder decoder model, which I explained in my last session. And you can again check that. Okay, this encoder decoder model, now at present, there are many kind of models in market. Some of these models, they use just encoder, some of them use just decoder, and some of them use both encoder and decoder. So you should keep in this thing in mind that GPT, I will show that what GPT uses and what BERT uses. So sequence to sequence models, they were very effective. They are still very effective in many tasks like question answering, language translation. And language translation, there are matrices of performance like BLUE. I will explain that. But again, sequence to sequence model, they have again some problem. which I will cover, and the attention will fix that problem. So there are two problems which the sequence to sequence model had. One was that uh, they were sequential, actually. They were based on LSTM or recurrent neural network. So what happened that if you have a long sentence which has 12 words, so you can process only one word at a time. So one word goes to the RNN unit or LSTM unit, and the memory state is updated. Then another word goes, memory state is updated, and so forth, one at a time. So that means there was a performance bottleneck. Although we have very high performance computing system like GPU, TPU, which are very good in doing parallel computation, but we could not exploit those architecture for the sequence to sequence model. So these were the two drawbacks. And then comes the attention mechanism. So sequence to sequence model still had this issue of not having very long memory. If you have a long sentence or a paragraph, so the context window was a bit small. Like many of you are using Chat GPT, and there is something called in context learning also option available in that. So where actually in Chat GPT, apart from asking your question, you can provide some context also, and there is some fixed size of that. So bigger context are always expensive. That one should keep in mind. So this is the background I have made. We started from data and we are there to the attention. So background language model. So this is very, very important slide. And I checked that even if you look at the professional courses, certificate program, and many other things, they will generally not cover this topic. Okay. The first thing you ask anyone that what is the language model? If someone cannot understand and cannot answer this question, what is the language model, then I think the knowledge is very, very superficial. So you must know what a language model is. So language model is a model or mathematical framework which gives you probability of a certain sequence of words or sentences. Okay, like here it was. Probability of this is fluffy dog. Okay. You give this sentence to a language model. This is a fluffy dog. It must give you some probability. And here it returns 0.132. Then you give another sentence to the language model. This is a purple flying bear. And it gives you a probability of 0.00023. Means it's very unlikely. Okay. And one more thing, that this is not only for the sentences. This works for all kind of data like image also. You give one image to some image model. Now I will not call it language model. And it will tell you that what is the probability of it. Like there is a website called this person does not exist. You check that website. You check the ethnicity, gender, age, and click on it. It will show you one image. Okay. So all the images which are produced at that website, they have very high probability of being real. Okay. So that is the image model. Like even if I check with like Indian person, this age group, you perfect. The probability is very, very high. So these are the generative models, which I will cover maybe in the next session, how you generate text and images. So that's under context. But here this thing is very clear that language model, they must provide some probability of any sentence. Now there are two parts. One is that just probability of this sentence, this purple is this is purple flying there. And second thing is that condition on it. I mean, I don't have time to cover the Bayesian formulas. Again, it is there in one of my past lectures and conditional probability definition. But generally, when you ask anything to Chat GPT is giving you answer, but the answer is conditioned on your question. Okay. Whatever prompt you are giving, that is what you are giving the condition. If you are familiar with Bayesian formula, it should not be a difficult thing. Now conditional like guess missing words. So how these model are trained, these language model, they can be trained in many different ways. I give you three examples. You have a huge corpus of data. and like guess missing words. This dash a fluffy dog. Now you find the probability of all the words coming at that uh, blank place, all the words which are in your vocabulary, and out of them you will find the probability when there is each is highest, and then you predict the word must be each. And mathematically, if you are familiar with Python, this argmax, I think you should be familiar with argmax. What it does is that if you have a list of numbers and if you give it to the argmax function, so argmax will give you the ID of that element which has the highest value. Like you have 2, 8, 9, and whatever number. So the argmax gives you that ID. Another example of training language model is the predict.
Can you explain a bit about argmax? What is argmax and new to that?
Argmax, let's just think about a list of numbers. Okay, like 1, 3, 5, 0, or 9, and then 4. If you say that argmax and give the list to it, so it will give you the position of the element which has the highest value. Like simply max gives you the maximum element in the list. If you say that max list, so whatever number is the maximum, it will give you that. And argmax give you the position. Like if people are sitting here, for example, and they have different height, okay, and if I say that argmax to this height, so it will give me the chair number where the person is sitting. It will not give me the person's height. Correct? So that's argmax. And predict next word is under task. Again, we can maximize that, and answer questions is also that. So basically, we are trying to maximize this conditional probability, and it fits perfectly well in if you have some background of maximum likelihood estimation and Bayesian formulas, then these things would be easy to follow, because this Bayesian formula and Bayesian model sits at the heart of all these machine learning models. So I think now all of you should be clear that what is a language model. And when we say that large language model simply means it was trained on very large data set. And these probability, they don't come automatically. They need to be learned from the corpus. Now let me come to the sequence to sequence model so that we can motivate the case for attention. So what was the problem with this? So it has two pieces. One is called encoder and one is called decoder. So we are trying to learn the language translation, English to French, for example. So our data set consists of pairs of sentences in English and French, few thousand, 50,000. What we do in the first encoder part, we feed English sentences one by one and one word at a time. Like the first case, first sentence, the first word will go how, and the memory state will be updated. So there is a vector we are updating. The C and yes, they are the vector. So when how goes the memory state is updated. Now, when we feed the another word R, again the memory state is updated. Past is taken and something is it, and so forth till all the words are finished in our sentence. So we have learned the context in terms of a vector which is called H, which is joining these two pieces, encoder and decoder. So all the information from the input sentence is now coded in one vector H, which is a context vector. Now we are ready with context vector. Now we have to produce the translation in French. So what we do, we start the starting token, whatever it is, and it predict some word. For this case now, we use that context vector because the decoder is also made of LSTM units and it has these memory states. Okay, so we have to use this context vector plus the current output gives me the next output in the decoder, and then my decoder state is also updated. So we keep doing this thing and then it produces the full sentence, the translation at the end. So that is how this works. Now there are two phases. One is the training part and one is the inference part. So when we are actually doing the training, then what happens that when the decoder is predicting the next word, it already has one word, like it has I or whatever. It already have the one word. It is predicting the next word. But if the next word, what is predicted by decoder is not the correct one, so we don't consider that word. We consider the correct word because we know that in the training phase, we know what the correct sentence is. So this is called teacher forcing. So that is kind of teacher is giving some assignment to a student and student is giving the answer. So if the answer is correct, so teacher is not considering that answer. Teacher is telling student, no, this is not the answer. This is the correct answer. Now you go with the next question. So in that way, teacher is actually giving the feedback to the student. Like student write 5 plus 4, 8. So before giving the next question, teacher correct, it's 5 plus 4 is 9. So in that way, decoder is also learning. I think this mechanism is clear here, correct? And the bottleneck is that the full information of the input sentence is squeezed in one vector, one context vector. That is the problem. So it is not like in order to produce the third token in decoder, maybe the first word was more important and second was less, and so on and so forth. So it is not giving any weightage to input tokens when producing output tokens. So a lot of information is just squeezed into one fixed size vector. So that's why the trans.
Does it remember the vectors that is pushed at the starting? So let's say there is a vector of I.
It updates.
So how it happens?
See, there is H vector. When it begins with, it has random values.
Yes.
Correct. When the first word comes, its value is updated. Second comes again updated. Third comes updated, but we are forgetting the past.
Okay, that's what I'm.
Yeah. So we are not.
The previous vectors got vanished.
Yeah, yeah.
It's vanished.
So it's like you when you are adding numbers, when you get a new number, I mean you are for you are spending money, for example. So you spend 200 rupees, you spend then 50 rupees, then you remember only 250. You don't remember earlier it was 200. Then you spend say 600, you just add on that. So you are missing the. I think that is clear here, correct?
So is that a problem with this model?
Yes, this is a problem. This is a problem. It is, as I said that, for example, I give you an explicit example, you are spending money. Okay. If you are keeping track of only the final amount, then obviously you are missing a lot of information. Correct. There may be something when you actually spend 350 rupees and you want to keep track of that also. So it may be better that you keep track of both the final amount and the intermediate. That's what exactly the attention does. Okay. This bottleneck. Look here at the example at the right, there is a picture and there are words in two different languages. It's a translation. So what happens, and the white bright are the higher values. So for example, let me come to that 1992. So when the decoder is producing 1992, so it's very much dependent on 1992 input. It's just popping of that. So in that sense, when the 1992 is produced, actually there should be more focus on 1992 in the input. Okay. So what I am saying that when different words are produced by decoder, this fact should be kept in mind that different input tokens, they should have different weights. All should not be just summed over. So for that, we have attention mechanism. So attention mechanism is, it gives you a provision to focus on certain words or give them higher priority when producing output tokens. So here it is. So in Teams, it is recording, I guess. Yeah. So now let me come to the attention mathematics. So it's bit of dense, but I will explain it clearly. So there should be no issue. First one is it's the joint probability of getting a sequence. I showed you in the earlier example that when there was a sentence with tokens, so that had some probability language model. So if you look at this, so there is a chain rule of probability. Like when I say that the sky is blue. So firstly, I produce the word the. Now in the second case, I try to predict the next word given that I already have the first word the. So it is condition on the word. Now when I produce a third word sky, blue, I already have two words, the sky. So they go after that vertical line in the right hand side when YT, and there is a all the past tokens there from Y1 to YT minus 1. And the C is the context vector. So it comes from the encoder, hidden state. Now what we do, the second point is important here. So for the context vector, let us assume that we don't forget the updated memory state when encoder is consuming the tokens. Okay. So we keep track of all these intermediate states. When the first word goes, we can call this H1. When the second word is inside, then we call it H2, H3, H4, H5. Now we have all these context vector and we do some weighted sum of these vectors. Now these weights need to be learned. Now we have a mechanism by tuning the values of these weights or learning the value of these weights, we can focus on certain words and ignore other. I think it should be clear here. The only confusion here may be that how one will know the value of these weights at the very first place. Okay, so this is the part of whole neural network architecture. Like you may ask this question, so what about embedding matrix? How you will know the value of embedding matrix at the first place? So the answer is that embedding matrix are also part of neural network and they are considered just like weights. They are not treated separately. They are part of the weights. And these things are also these coefficients, attention coefficients are also part of the network, but there is a formula for learning them. So it's a soft max. So there is a mismatch. This alignment model. So what it is trying to do is that for now, let us consider we are producing a token in decoder at let us consider it jth position or yeah jth position. We are producing a token in decoder. So for that we need attention coefficient for all the intermediate states of encoder and their coefficients. And here this formula in the last line, you can see that the denominator is just normalization. And this gives us those values of coefficients. I will come on this thing again and again. Okay, so you can again ask what about the weight? And this is the program I have put there. It's on my GitHub page. It's a Jupyter notebook. It shows the LSTM plus attention. So I have three exercise here, three notebook or the same notebook. By commenting three different line, we can do three exercise. So there are line number 48, 49, 50 in this. So when I switch on line number 49 only, so I am using a simple LSTM unit. And this is a program for the classification, task, sentiment analysis, 0 or 1. So let me explain the neural network architecture. So 46 line is consuming the input sequence of words. Its size is maximum sequence length. Generally, we do the padding also. After that, it goes to embedding layer. Okay, and one embedding layer takes IDs of the input text, like 1 to 20,000, 30,000, whatever. These are IDs. Okay. So every sentence is made of words and we have ID for every word. Now, once it goes inside embedding, after that, what comes is are the vectors. After that, these are fixed size vector, latent dimensional size vector. Now this vector goes to LSTM, and this LSTM, we have written that return sequence is equal to true. So LSTM returns me a sequence, and then I apply one dropout on it and the dense network. So finally, I get just 0 and 1. So this is just plain LSTM. So this is the result I get for the plain LSTM. The result is not very promising because I used very small data set. This is just to show how the architecture and the mechanism work, not the performance. Okay. So here are the layer at the left, input layer is there, embedding layer is there, LSTM, dropout, output. In case you are still not clear about this number, I can explain later on, or you can try to figure it out, that the number of parameters, total number of parameters, how one finds the total number of parameters. Okay. And at the right, you can see that loss is coming down for the training part, but not very much for the validation. And accuracy is going up for the training part, not for the validation. So that's another issue, which is not here concerned. Now, the same code I can change into another exercise. Now I comment out the line number 49 and I switch on the line number 48. Then it becomes a bidirectional LSTM. So what is a bidirectional LSTM? So LSTM layer generally it runs from left to right. Sentence says firstly first word goes, then second, and so on. So if you have a bi LSTM, then you will have actually two layers. One is going forward and one is going backward. And the output can be concatenate. If you are not familiar with this operation, if you have two vectors, so there are many operations you can apply on these vectors. The simplest one, the scalar product, which gives you a number. If they are of the same size, you can just add or subtract them. There is one called element wise multiplication also, that is also used in vector. And one is called concatenation, where if there are two vectors, so we just put these vectors next to each other. Like if a vector is of size 4 and there is a size of 5, so resultant vector will be a size of 9. So it is like 3 chair and then 4 chair, you are just making a bigger line. Concatenate is very liberal. Generally, you don't lose anything. Basically, you are keeping track of everyone. Okay, so wherever you are doing concatenation, don't worry much about. You are not losing anything. The problem is that you will be keeping still the number of weights higher. Correct. You are just arranging them. But when you are using other operation, then you should be thoughtful.
Could be anything because in bidirectional, if one element is multiplied with other element, it will be the value will be more.
Yeah, so
the
that may
context
be
will
problem.
also be changed.
Yeah. The multiplication, element-wise multiplication, one should be very careful. It is not always available. Okay, like in LSTM, we do certain things because as you are saying that things may get mixed up. But concatenation is safe.
Situation element-wise multiplication is better.
Now it comes from research. Like when the LSTM unit was proposed and the gates were proposed. So these gate, they get multiplied with the vector. Okay, so there are element-wise multiplication. So it comes with some research, but concatenation, you can just do it basically. So as I said that the same Jupyter notebook for 3 exercise. Exercise 1 only LSTM. Exercise 2 switch on the bidirectional LSTM and switch off the LSTM. And third is switch on the attention mechanism. So there is one attention also. I will show the attention function. So this is LSTM and this is bidirectional LSTM. So what you have to check is the number of parameter. Here it is 63, 20, 65. It is 66, 41, 29. So number of parameter have increased. Obviously, we are putting another layer there. Okay, now we are putting attention. So this is bidirectional LSTM plus attention. So I'm not showing code because it's the same code, but it looks that it gives better performance roughly. but we can't contest that very much because the number of parameters also increase. Let us, I don't have that number, but obviously there will be more parameters. And this is the attention function. It's very simple. If you are familiar with Python, what it is doing, it is taking one input vector x. Look at the third method, and then attention mechanism is having its own weight and bias, and using them and returning under vector. Okay. So this was the attention mechanism used in sequence to sequence model. So there were 2-3 papers in this where sequence to sequence LSTM was there, but attention was also used and people got higher performance. But again, it was not solving the purpose because LSTM was a bottleneck. We still need to do things sequential. Then there came the transformer mechanism, and it was proposed in 2017 by Google team, and Ashish Vaswani was the lead author of this paper. And this paper is one of the most cited papers in computer science. Historically, I will show the number also, I think 92,000 and more than that. Just in 6-7 years, it got that many citations. And this paper was the foundational paper for all these LLM models which we see nowadays. Without this paper, we would not have GPT or anything. Okay, so this was the paper. Attention is all you need, and the title of the paper was also quite catchy. Attention is all you need, and you can see that it has 91,000 plus citations, which is a very big number. So the main claim of this paper was that we can get away with RNN LSTM completely. We can make a framework or neural network architecture which will use only attention mechanism and no recurrent neural network. That simply means no bottleneck of sequential computation. These attention coefficient can be computed in parallel. So that will accelerate the process. And simply means like the large language model, when we have huge data volume and then we have GPU. So this was a perfect match where GPU were hungry to do computation in parallel, and this model was hungry to do things in parallel, basically. So they just met, meet, and very good performance was achieved. And they claim one score called BLEU, blue score. Let me come on that, what that is. So the task is machine translation, neural machine translation. You have a computer code which can translate sentences from one language to another language. So in order to quantify the quality of translation, this matrix was developed. And what it does is that there is one sentence which is coming from computer translated. It compares that machine translated sentence with a set of human translated sentences. So there are 4 sentences, for example, and this machine translated sentences will be compared with them in terms of something called n-grams. So n-gram means single word, how many single words are matching in that candidate translation and the human translations, and then double pair called bigram. So in a pair of 2, and a pair of 3, and the pair of 4. So I have a formula later on at the end of this thing where you can get the numerical answer. But the claim was that this architecture gives higher blue score on certain language tasks, particularly related to language translation. So there are claims and there are numbers there. So I have tried to avoid giving these numbers. They look sometimes like advertisement or marketing thing that people give performance matrices, these, that, but you just have to believe with them. You don't know what is what. Correct. So there is a very good number of advertisement also in this paper. So transformer key points. What are the key points? Selling points or transformer are based on encoder decoder architecture. That is fine. So those 2 boxes remain the same. No RNN LSTM units, which are hard to parallelize, are used in transformer. So completely scrap. Transformer use a mechanism called self-attention to relate the tokens in a sentence. So that I will explain what is the self-attention. Since self-attention does not consider the order in which the token words are used in a sentence, so a new mechanism called positional encoding is used. So what is self attention is that you have a sentence and you align that sentence with itself, and you relate all the pairs. Okay, so how it helps, like when you are speaking some sentence, long sentence. Okay. So at ninth position, whatever word will come, that will have some relation with some word which came in the past in the same sequence, or more than one words. So which of the words are more important for that word? So that thing is the self attention within the same sentence. Not so it is like it's a kind of self learning or self supervised learning.
To give more importance, it knows itself.
Yes.
On the biggest.
Yes. So like when you speak something after uh, in the beginning, I will tell your name, Satya, I said this thing. After that, I will start using it, he, or some pronouns.
So the output of the self-attention will be the sum of the weighted vectors.
Yes, some kind of. I will show you with the equation. So now this is very important, and it took me quite a lot of time to actually understand it, because if you look at the actual paper, it is not clear in the first reading what does it mean by query key value mechanism. So this attention we will call query key value attention. Okay. So what you do, like when you search any database, so there is index or key and value. Let us think about a database which is made of key value pairs. So your query is generally a key, correct? You can correct me if it's not clear. So your query is a key, and your query will be matched with one of the keys in the database. So it's called hard indexing. When your query perfectly matches the key, the value will be given. Okay, so this is the normal kind of hard indexing system. So key, value, and then there's a query. Query comes from outside. Key value is a part of data point. If you make any sentence, okay, on that, or a long paragraph, on that long paragraph, I can decompose this paragraph in terms of a set of questions and answers. That should be very clear to you, which will be equivalent. Like you have a paragraph. What I am saying is that you reduce that paragraph into a set of questions and answers. Okay, so next time when anyone asks any question, you match that question with the questions you have. If it matches, you give the answer. Now in computer science, I am just diluting it. I am not saying it question answer. I am saying key and value. So whatever information you have, whatever data you have, just split it or decompose it into key and values. So now your all the data is in key and value. Okay, and whenever the query comes, you match with the key. Now there is called soft attention. I said that the hard indexing and there is a soft indexing. As a soft indexing, a new mechanism which comes in neural network, and this like embedding. I said that in place of having a hard vector for a word of made of 0 and 1, where things will match or not match depending on 0, we have a embedding vector which is a soft vector, which can give you similarity with any kind of words. If you say that the elephant and mango, okay, so it's not hard matching them, but there will be some similarity. We have the soft vector embedding vectors. Cosine similarity you find, or you whatever you prefer. Correct. Now think about here in this key value pair. these key and value both are soft vectors. Okay. Now we are not talking about tokens and sentences. We are talking about vectors. Your key is a vector and your value is also vector. Now, what about if your query is also a vector? Then what you will do in that situation? You will match your query with the key cosine similarity. Okay, or in fact, there are your database has 20 keys. Okay, query comes, you just match with all the keys and get the cosine part of it. And that can work as a weight. So once you get the weight for all the keys, you can multiply that with the corresponding values and you return the answer. And that is your attention. So I think it should be very clear now. This is a fairly complex. Now come to the how we do that. That what we have is for every encoder token, when it goes in encoder, it has a memory state H. For every word, we have an H, correct? So that H, we can map H to three vectors Q, K, and V. Query, key, and value by multiplying them with three different matrices of appropriate size. And again, here these matrices will be learned. They are not given from very beginning. Now, one single vector, this H, the state, memory state, is now converted or decomposed into three vectors, Q, K, and V. Now think about that every token in encoder is now holding three things with itself. It has a Q, K, and V. So whenever any query comes, like think about in decoder, if we are decoding the fourth token. Okay, and in encoder there are 10 tokens. So that fourth token will launch a query. Okay, and this will get hooked with all the keys in the encoder and get a value of attention. I think this should be clear. And now if you go and read the paper, you will better understand it. So same thing is here that in this pictorial way, at the bottom, you can see that there are three matrices which are mapping that green vector, which is the state, into three different color vectors. Okay, and here also you can see that at the right bottom that picture, the self attention is then again it is using this self attention weight to different tokens when producing the output tokens from the decoder. So more will come here, but at this point, I think it's clear. Yeah. Yes.
That is
Blue is query key value. So one vector goes into three vectors. Now self attention, how much attention a word which provides Q. Now mind this thing, which provides Q means we are talking about the decoder when it is emitting any output token. Okay, gets from underworld which are in the encoder, provided K and V value depend on attention coefficients. We have seen that it's a mathematical operation. It's just a, if you look at the equation, the Q and K are scalar product. Okay, in the last equation, Q and K, QK transform, it's a scalar product. It is divided by dimensionality of the vector to normalize it. And then it is applied on the V, which is a vector. Note that attention matrices need to be learned during the training. In place of using a single attention head, it has been found to use multiple attention heads which can encode different type of context token can provide to each other. I will explain this thing. This multi-head attention. The first thing was the attention itself was sufficiently complex to understand, but then multi-head. So what happened that even there are two tokens, okay, in a single sentence. So they can have different multiple relationship between them. I will give you a human example of there are two individuals. Okay. So they can be friend, they can be some other relation, can be student teacher relation, can be there, some family member. So like two words also when we are uh, for different purpose, okay, for different purpose, different kind of relationship between these two tokens may be needed to answer the question. If you say that like
Is for that
a
particular
multiple head,
oh,
so it
is
will
that
discover multiple relations.
based on the probability of which query being asked, it will select the respective values or keys.
Yes, yes. So I think this thing clear why multiple head. We are not limiting one kind of relationships. Okay.
What is the black box?
Black box thing means
Like, see that there will be a black box in every machine learning algorithm or something.
black box thing is that the information flow. It is a very big network of millions of parameters or billion now. I think they are touching trillion. I was checking something. So it's not clear that inside it how information actually flows. So you have to trust only that it works, so it works. Okay, and again, there may be provision that if you change the architecture, okay, you may get better performance than the existing one, but you have to do very big experiment, which may cost millions of dollars. Just to challenge any such model, it will be. That's why this Open AI boss, when he was Indian people asked him that whether Indians should also try this large language model. He said that it's a hopeless, but you can still try. So some people got offended with that. So multi-head attention, you now the first thing was attention, and then second was multi-head attention. So why to limit? So multi-head attentions means there will be multiple weight metrics. So encoder self attention. So now what we are doing when we are at the encoder, okay, we are finding the uh, attention between all the tokens in our input sequences. Okay, so this is shown in pictorially there. But when we are in the decoder, then we don't find the attention between the current token we have and the tokens which will come in future. That will not be appropriate. Okay, so you can see that it is cut, it is asymmetric. So it only look at the past tokens. So this is multi-head attention. You can see that now was single memory is state was split into three vectors P, K, Q, and further then they ran in parallel for multiple head and scalar dot product attention. It's a scalar dot product. I mean, it's obvious basically. It's just scalar two vector scalar product. And at the last, you can see that it's a concatenation. So we are again not mixing the information from multiple head. We're just keeping them, aligning them one after one. Okay, and after that there will be the linear layer and the dense layer. So here it is pictorially, it is shown. Okay, and when we reach at the top, then it becomes a usual machine learning. We have a dense network. Now, positional encoding, again, this is another complex topic, and I will explain it also. So when we are computing the attention between different tokens, we are not capturing their relative position in a sentence. That you can imagine that if you have a 5 words, 1, 2, 3, 4, 5. So you will find all the pair between 1 to 1, 1, 2, 1, 3, 1, 4, and so forth. But it doesn't capture the sequence that 2 is coming after 1 and 3 is coming after 2. Okay. So somehow in order to capture that, the position is also mapped to a vector. Okay. It is called positional embedding. So one separate vector will come that will represent the position. Mathematically, I will explain these equations are quite interesting at the bottom. So you all are familiar with this cosine and sine functions, and particularly in the context of Fourier transformations. Correct. There are frequencies. You can pick them, different frequencies or harmonics. So, I mean, they are used in all the cases like signal communication. So here what we do, POS is the position. Okay. And the position can be from 1 to 10 if the sentence has only 10 tokens. Just assume that. And 2i, I is the dimensionality. Now our embedding vector may have 300 dimensions. So I will go from 1 to 300. Okay. So for every position of the token in a sentence, we are computing the components along the different direction of embedding space. Okay. And you should convince yourself with these two equations. Obviously, 2i will take care of the even case and another will take care of the odd case. But at the end of the exercise, what will happen that every position will be uniquely represented by a vector of the same dimensionality of the embedding dimensions. So we secured the positional information also in this mechanism. So we have the memory state, we have the attention also got converted into a same dimensionality of vector or appropriate dimensionality of vector, and we got this positional encoding also as a vector.
So how do we relate the position of the token?
Now that comes in the architecture. I will show the architecture. Okay, in a black boxes. So this is the architecture. It's a very famous architecture of attention. It has two modules. At the left, it's the encoder. At the right, it is decoder. But you can see that once the attention part is done, then there is a positional encoding. Even before that, there is a positional encoding. If you look from the bottom, the first input goes in and immediately positional encoding is applied on it. Okay. And then it goes to multi-head attention. And then linear layer is there. So in a very broad way, what is happening here also, at the left, encoder is creating contextual information, very rich contextual information. And that information is being fed to the decoder. Okay, when the output is generated. So there are some cases like in GPT, other where we don't have both the pieces, we have only one piece, but most things work as usual. So there was a very famous architecture. It came in 2018. It was BALT. So before GPT made noise, BALT was there and it made a lot of noise. So two things about BALT. One thing was that again, it was completely based on the attention network or the no LSTM, no RNN, completely parallel. And second thing was that this BALT model, again, it is self-supervised. I will explain what does that mean. And it had, it was bidirectional, like bidirectional LSTM, left to right, right to left. So it gave many advantages. Okay, to give the context, basically, I mean, we could get context from future also for the current token. Although there are safeguards that it doesn't look into itself. Okay, but the advantage, one advantage that they claim that this bidirectional thing was quite advantageous. And then it was completely based on attention and self-attention. And now this thing is quite common, this pre-training and fine-tuning nowadays. So what happened that any big large language model, it has two phases. One, it is the pre-trained on some data, some other task. Okay. And later on, it is fine-tuned for some particular task. So BALT claimed, you can see that these are performance matrices of it. And it also has very high citation, 79,000 plus citations since 2018. And there are still BALT model available. People are using them. And in fact, if you survey the landscape of large language model, you will find that BERT still captures a fairly big territory, maybe 30–40%, and the GPT, and then there are a few other.
What is GU score?
There is a benchmarking data set and mechanism. I mean, I also don't have much information, so these are standard benchmarking problems, like this SQUID, Stanford question answering data set. So it claims very high performance. So BERT stands for bidirectional encoder representation from transformer. BERT is designed to pre-train deep bidirectional representation from unlabeled text by jointly conditioning on both left and right context in all layers. The pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of tasks, such as question answering and language inference, without substantial task-specific architecture modification. So BERT motivation, why someone was motivated to create BERT. So there were two kind of models at present. One was that feature-based, for example, Elmo was there, use is task-specific architecture that include the pre-trained representation as additional features. So it was task-specific model you train and then you use it. Second was the fine-tuning approach like GPT, introduces minimal task-specific parameter and is trained on downstream tasks by simply fine-tuning all pre-trained parameters. So GPT and BERT came almost at the same time in 2018. In fact, GPT came before that, but that time BERT made more noise than GPT. Both the above techniques restrict the power of pre-trained representation, especially for fine-tuning approach. The major limitation is that standard language models are unidirectional, and this limits the choice of architecture that can be used during pre-training. So GPT is still unidirectional and BERT is bidirectional. So BERT has two kind of training. Very simple, anyone can understand. Masked language model. So you have a huge corpus of text from Wikipedia and various places, wherever you get it from, and you mask certain words in sentences, and you force BERT to predict those. So you should think in terms of maximum likelihood estimation. Basically, I will again give an example just to make it simplify. That you are doing one experiment, you are measuring heights of people in a sample, 100 to 100 people. Okay. So from these heights, you can get the mean and variance, mu and sigma, and then you plot one thing. Okay. So what you are trying to do is that with your data, when you are measuring next height of someone, you are trying to tune this mu and sigma. And this is how you are learning it. And finally, you will have a robust mu and sigma from which you can create a distribution of heights of people. So this is the same way that you are forcing or you are tuning the parameter in such a way that the masked word is correctly predicted. You can always do that. There are millions of parameters. Okay, you can always tune them in such a way that I gave example, the sky is blue. If the sky is masked, so you tune these parameters such a that the probability of getting their appropriate word is maximum. So this is the masked language model. So this was one component. The second component of BERT was that next sentence prediction. Now you have millions of sentences. You force it to predict the next sentence correctly. So when I say that you force means you tune the parameter. Okay, by running this back propagation or some algorithm. So these two tasks, and along the way, what will happen that when you train the BERT on these tasks, you will actually have a very good embedding also. Embedding for the text or words, and you can use those for whatever task you want for other tasks, downstream tasks. So this was the BERT component and fine tuning. I am not going in that. So if you look at the data, so it has a token embedding, segment embedding, and position embedding. So this is very important that it's creating very rich information. The positional information is there, even the segment. So when we discuss the word to back or word embedding, so no one stops us from learning the embedding for the full sentence or the paragraph also. And they will be also the same dimensity. So they can be incorporated in the network.
So what is segment like? Does it take more than word? Does it?
Yeah, more than word. I think they mean this thing also that sometimes there are out of vocabulary words. I will again confirm that. And if they don't have embedding for these words, they break them into small parts. And sometimes these small pieces actually they have the embedding available. So words and others. So these are the different architecture and the performance claims are there. Total parameter in the left bottom, you read that BERT large, it had 340 million parameters. So that time it was very big or the biggest. Now we have much more bigger model. So GPT came at the same time, improving language understanding by generating pre-training. So the GPT family of models, they generally have two pieces in their training. One is the language model, the probability, and second is the fine tuning. Okay. I will explain. GPT is based on transformer architecture. Let me see what was the claim here. Claim where that those number how much performance they got. GPT provides a more structured memory for handling long-term dependencies text compared to alternative like recurrent networks, resulting in robust transfer performance across diverse tasks. So two stages, as I mentioned in GPT. The first stage is learning a high capacity language model on a large corpus of text. So this sentence is clear in itself. When I say that high capacity language model means the probability of all probable sentence is correct and very good. Okay. And probability of all the sentences which are not there anywhere and which do not make sense will be very low. So it will not generate text which doesn't make sense. And the example is like ChatGPT. The probability of ChatGPT generating some sentence which does not make any sense is very, very less. So language model is very strong. Second thing is its second stage for fine tuning stage, the model adapts to a discriminate task and labeling data. Now discriminate task may be translation, question answering, very specific task. It can be fine tuned on them. And again, this is the same equation, the language model I have already shown. You can go back and again check this equation of conditional probability. Basically, this PX is the language modeling is usually framed as an unsupervised distribution estimation from a set of examples, each composed of variable length sequences. So what is the probability? Okay, so I'm not spending much time on that. GPT, because it's a new model, so I have highlighted many segments on a different color, just to emphasize. The first thing is that we explore a semi-supervised approach. Okay, it's a semi-supervised, no label text approach for language understanding task using a combination of unsupervised pre-training, it's a language model, and supervised fine-tuning. So it's a combination of both. So there will be some label data for the fine-tuning, but there will be unsupervised. Unsupervised means just text corpus. Our goal is to learn a universal representation that transfers with little adaptation to a wide range of tasks. So that was a tall claim basically, that we want a universal representation irrespective to the any particular task and which has a very high generalizability like human being, where they can make all kind of sentences. We assume access to a large corpus of unlabeled text. So this is the requirement part. What they need, large corpus of unlabeled text and several data set with manually annotated training example. This is also important. For the training purpose, they needed both. You can check in the literature. They needed this uh, unlabeled data like Wikipedia, but they use some labeled data also. Okay, our setup does not require these target tasks to be in the same domain as the unlabeled corpus. Okay, so This data set for the fine tuning, it may come from any domain, and for pre-training, it may come from any domain. So it is not like, for example, there are some version of GPT and some large language model which are trained on medical data only, medical text. Okay. But it claims they can be different. So, for example, yeah, it is there. I will say. Okay. We adapt these parameters to large tasks using the corresponding supervised objective. We evaluate our approach on 4 types of language understanding task. Okay, so this is the test. How to know that it is working? They tried it on natural language, okay, question answering, semantic similarity, and text classification with natural language inference. Our general task agnostic model outperforms discriminatively trained models that employ architecture specifically crafted for each task. So out of 12, they do good for 9 tasks. So I'm not going in this technical detail, but this is exactly the same thing where unsupervised language model. And now came GPT-2. So within 1 year or 2 years, they release this under model GPT-2. Natural language processing tasks such as question answering, machine translation, reading comprehension, and summarization are typically approached with supervised learning on task-specific data set. Okay, so what was the special? So this is the detail of that. Yeah. That's generally what is happening in GPT broadly. From GPT 1 to 2, 3, 4, architecture is not changing much, but the number of parameters in data set is increasing. So that is the trend. Okay, like GPT-2 is a 1.5 billion parameter transformer. 1.5 billion, big number. And there is this technical thing, the zero shot learning. So zero shot learning means without providing any in context thing. You just ask question, get the answer. Okay. And one shot learning is give at least one example. If I ask you a question and you ask me, please give at least one example so that I can answer. That's one shot learning. And then GPT-3 came. Okay, and GPT-3 was able to consume all kind of data. If you read here, I think there were images, quotes, and various kind of things were there. Okay. Pre-training on large corpus of text followed by a fine-tuning on a specific task, and the number of parameter will again be large. And then this was the performance. Few short learning, one short means at least one example, few short means few example. And GPT-3, I'm just showing the number here in this table. You can see that how many parameters these have. And in between, GPT has other models also, like between 3 to 4, there will be something between. And BALT is also there. So they are comparing BALT also. Okay, petaflop per days. Now let me explain this thing. This is a big business. Training these large language model needs a lot of money. And I don't know if you're familiar with this unit of computing flops. If you are not, then I will tell you flop means floating point operation. So generally our processor are running gigahertz clock, few gigahertz. So typically you can say that 1 gigahertz is like 1 gigaflop. Okay, then it will go to teraflop and then petaflop and so on and so forth. So 200 teraflop is like a big cluster of thousands of processors. And these are many models. GPT training cost is also given there. So it needs few millions of dollars to train it. Now finally came the GPT-4. And with many things are not being disclosed in public domain, people are becoming more and more conservative basically in disclosing the technical information. So they publish this 100+ pages report, but like not everything is, it looks like mostly marketing and other kind of stuff, but technical information is there. And after GPT-3 takes codes, images, text, all kind of data it can create and produce also.
But GPT-4 is not a language model. It can
Yeah, it's written there. I think you can check it. Yeah. Okay. We report the development of GPT-4, a large-scale multimodal model which can accept image and text inputs and produce text output. Okay. I will give you an example because I am not covering its technicalities. Uh, there are some shortcomings also which are known, like it's not fully reliable hallucination. It creates some fake thing. Has a limited context window. Does not learn from experience. So these are the but biggest selling point of GPT-4 was that it was able to clear many international exams with very high scores. Okay, these are the exams and these are scores. So GPT-4 was always in top 5 and 10 in most tough exams, law exams, medical exams, engineering. I don't know if
But
they
I
tried
think
with
it got
IIT or
trained in UPSC.
maybe,
Yeah, there was a news I saw.
maybe
Yeah, it got trained.
it got better. And GPT, you can ask this type of questions also, like, oh, what is funny about this image? You give an image to GPT-4 and ask, and it gives those answers. You can see that's a very odd image, like it's a phone, but this BGA plug is put on it, and so on and so forth. It is from the GPT-4 report.
You can give it to Bard also. Bard also.
Yes, it will do it. Or this one, what is unusual about this image? Okay. And then examples are there. You can have the prompts and it will give you answers of certain things. So key reference papers are these. It all started from 2015 when this attention is all you need paper came, Vaswani. Then 2016, the attention, uh, this came, attention, I think attention paper was later. Okay, it was in 2017, not in 2015. Okay. So 17 after that, mostly it is a transformer network. And we are at 2023. So just in a span of 8 years, so much happened. And maybe next one of my next session, if I give on generative AI, so I may be able to cover something that business impact of this genetic AI. What are the numbers people are talking about? So some references. So these were the. I will share this presentation. It will be there. You can check this tutorial. And blue score, this I shared this thing. So blue score is like between 0 to 1, but people have normalized it between 0 to 100. So up to even human being can't have more than 60. Okay, they also get less than that. But most models are getting in the range of 30 and 40. So, so these are kind of assignment, or you can think about it. I will share this thing that if you want to check your understanding, then what are the tasks you can think about? You can create word embedding with any neural network task such as classification. If you can do it, if you are convinced that you can write a Python code of 20, 30 lines and you can create your own word embedding. Okay. Like if you have a sentiment classified data set, you should be able to do that. And you can create a neural network classification model with LSTM layer in Keras TensorFlow. So examples, Jupyter notebooks are shared. You can go through them and check them. How sentiment analysis you can do with LSTM. Third is that you know how sequence to sequence model with LSTM works. So again, there is a Jupyter notebook. Okay. And then how attention mechanism can be incorporated into the sequence to sequence. And finally, the transformer. So I will just close this thing and maybe I will just show some Jupyter notebook. Then I will. So one notebook is this one, Jupyter by LSTM with attention, and one is the sequence to sequence. So I have written two sequence to sequence notebook. One is the sequence to sequence without attention. Okay, this one, and under is sequence to sequence with attention. So without attention, it is still doing good, some kind of and it is also doing fine, but not, it needs some more fine tuning. So I think now I will take questions.